Let's do our first nucleophilic addition to a carbonyl. Let's add water to a carbonyl. Hydration of a carbonyl will make a 1,1 diol, geminal diol, as it's known. If you know your astrology, you know where that comes from. Very commonly known as gem diol. So if I have two hydroxyl groups on one carbon, that's a gem diol. Also known as a hydrate if we got it by hydration of a carbonyl compound. But it's a hydration because look at the net addition here. We added an H and an OH. It's the net addition of water across a carbonyl like that. It is equilibrium controlled, so that means we can adjust whether reactant or product is favored depending on how much H2O is present. If I load this up with water, if I put a huge excess of water, we can push this reaction to the right by Le Chatelier's principle. Likewise, if I boil it and vaporize the water off or distill the water away, we can form the carbonyl. Or if I have a dehydrating agent that captures the water, we can bring it back to the left. But the actual equilibrium constant depends on the substance itself. Acetone with water is pretty much untouched unless it's forcing conditions. However, formaldehyde, even with a little bit of water, will favor the hydrate itself. So the formaldehyde that we know of is actually hydrated with water. Okay. So if we have formaldehyde in a water solution, we do not have HC double bond OH present within that solution that's been hydrated. We can do a base catalyzed or an acid catalyzed mechanism. The base catalyzed mechanism is the most straightforward. If I have hydroxide present with the carbonyl, the nucleophilic hydroxide will add to the carbonyl carbon, kicking electrons up onto the oxygen. So we get an alkoxide ion intermediate, which can be just protonated by the water that's present in the rest of the reaction mixture. That will give us our hydrated carbonyl compound, which is a gem diol. And in protonating that alkoxide, we have regenerated the base catalyst, right? That hydroxide ion catalyst. So very simple, 2 steps, but still equilibrium controlled, depending on how much water that we have in the solution. Acid catalyzed hydration is a little more interesting. It's actually a little more useful a lot of times. If we have an acid catalyzed reaction with a carbonyl, one rule of thumb is going to be that we will protonate the carbonyl oxygen first. So remember I said the oxygen is partial negative, so it will seek out one of the hydrogens on hydronium. So we'll end up with a protonated carbonyl right there, making water. This protonated carbonyl has a resonance structure. You don't always have to draw this resonance structure, but it's in resonance with a full carbocation. So the carbon of a protonated carbonyl is even more electrophilic. This is an activated carbonyl. The O plus sucks even more electron density away from that carbon. Just like in hydronium, the H's are the electrophilic parts. In a protonated carbonyl, the carbon is the electrophilic part. Okay? So by protonating the carbonyl first, we make this carbon electrophilic enough that a neutral nucleophile can attack it. Right? Typically, we do not have a neutral nucleophile just attacking a regular plain old carbonyl. We'll normally protonate the carbonyl first, which will then allow a neutral nucleophile to be able to attack it. So when water attacks that protonated carbonyl, we end up with an OH from the carbonyl. It kicks those electrons up, making a regular OH. But then we have H2O plus group attached to the carbonyl carbon. So another water molecule comes along, deprotonates that OH2 group, and that gives us our gem diol. So in these acid catalyzed mechanisms, look at what your goal is. We needed to add another oxygen, so that had to come from water. We have pretty much our product, but one too many hydrogens with the plus charge, so water can deprotonate just to make our plain old neutral hydrate product. We can do that same exact process going backwards with the same exact intermediates. All of these mechanisms, you should know them forward and backwards. All of the structures will be the same going forward and backwards. Arrows will be a little bit different, but the structures will all be the same. So if I go backwards here, let's start with just acetone hydrate, HO. Our second to the last structure had a protonated alcohol in it before, so that's going to be the first thing we'll do with our hydrate here. I'll react it with hydronium, which will protonate one of the alcohol oxygens. Make this as equilibrium arrows. All right. Our final product has only one oxygen in it, so that gives us a clue that this water will be leaving. That can be assisted by the lone pairs of the other oxygen. So I'm going to bring these lone pairs down to form a double bond, which will cause water to leave. Water is a good enough leaving group that if we need it to, it can leave on its own. But if I have something with a lone pair next to it that can push it out, that's a better mechanism to draw. Okay, so make sure you show these electrons going down, pushing the water out, right? Literally by making too many bonds on that carbon, so the water has to go. That gives us this, plus water. Okay, essentially protonated acetone. That water that we just released will attack that hydrogen and deprotonate. Okay, so same intermediates, but our arrows were drawn a little bit differently. So make sure you can do that both forward and backwards. Same intermediates, different arrows.